Anka, and I will be talking about simulation extractability of zkSNARKs. So,
Excuse me, please extend the microphone. We don't hear you.
okay, so I will start by describing our contribution, then I will go into NISC definitions because they matter actually for this talk. I will describe briefly a problem with an SRS. I will introduce you to some notions of soundness, and I describe what they give. Then I will explain what simulation extractability is and how to build an extractor for zero-knowledge SNARKs. So in this paper, we define simulation extractability for updatable NISCs, but also for NISC like with general SRS and random particles. We analyzed three properties that are needed for NISC, for zkSNARK to be simulation extractable. And we show that the wide class of already deployed zkSNARKs are simulation extractable out of the box. And this is nice because we have like a number of framework that lifts security of zkSNARK to simulation extractability. But what is nice in our result is that we show that, well, you don't need to introduce any change to your zkSNARK to have simulation extractability. So you don't have any security, any efficiency loss. Last but not least, our contribution gives snarky signatures of knowledge in the updatable setting. Okay, so let's start with some zkSNARK properties. So as usually, we have some NP relation where X is the statement and W is a witness, and we have a prover that knows some SRS and gets as input X and W and sends proof to a verifier that knows only SRS and the statement. So first of all, we require from our zkSNARK or NISC system in general to be complete, meaning that a proof generated by an honest prover should always be accepted by an honest verifier. Then we have knowledge soundness, and this is quite standard what you are showing currently in zkSNARKs. It means that a verifier, if verifier accepts a proof from a prover, that means that the prover, not only that the statement is correct, but also that the prover knows the witness. And formally, we prove that by showing existence of an extractor that can be like adversary or prover specific, and gets some public parameters, SRS, prover's randomness, and in the end it outputs the witness. Last but not least, we have zero knowledge property, which basically states that the verifier learns nothing besides the veracity of the statement, and formally we define zero knowledge by introducing a party called simulator that is able to produce proofs indistinguishable from proofs of honest prover. And since we are in zkSNARKs, we also require succinctness, meaning that the proof has to be sublinear to logarithmic to the size of the state. Okay, so our result works in the updatable setting. So let's discuss for a moment like all problems related to generating the SRS. So in zkSNARKs that rely on SRS, we have a keygen procedure that takes public parameters and output trapdoor and SRS. So trapdoor is sometimes called like toxic waste, and it is necessary for the simulator to simulate, usually. Okay. So the first approach could be like, okay, let's have some trusted party that generates the SRS. But in this case, it's quite problematic because if if the trusted party becomes malicious, then it can generate proofs for even incorrect statements. So in real life, we often have like MPC ceremonies that generate the SRS. And recently, we also have this updatable setting where basically everybody can take the SRS and update it. So generate a new SRS top of the old one, such that if at least one party that updated the SRS was honest, then the whole SRS is secure. Okay, so let's briefly discuss how zkSNARKs are built. So we on the left we have prover, on the right we have verifier. So what prover usually sends is some set of polynomials. The verifier responds with some challenges, and this communication goes on. And eventually, the verifier sends some challenge Z. Some call it evaluation challenge. And the prover responds with evaluation of the sent polynomials at Z. Okay, and in the end, the verifier checks some equality on Z and PI evaluations. So to get from interactive to non-interactive, we use a Fiat-Shamir transformation. So instead of prover sending polynomials to the verifier, prover computes the polynomials itself by querying a random oracle. So on the transcript. So instead of sending P to the verifier, prover computes alpha 1 itself, such that the alpha 1 is a random oracle output on the transcript. So it's a statement and the first message in this case, right? And in real life, we usually we don't have random oracles, and we know that we cannot have them, so we use hash functions. Whether a hash function is good to have here security is another question. And this communication goes on, so the prover computes the challenges itself, and eventually it gets the Z and computes the evaluation. Okay. So what prover actually sends to the verifier is only these polynomials along with evaluations, and then the verifier, say, locally queries its own random oracle, which is the same as the random oracle of the prover, and verifies the statement. Okay, so let's look at the definition of knowledge soundness. So we in this model, we assume that the adversary has access to some random oracle and some gets its input some public parameters, SRS, and also has some randomness, right? And eventually it needs to convince the verifier on some statement. So this model doesn't fit really well to reality, where the adversary may not only has access to the random oracle, but also sees a lot of proofs, like, say, flying around in the space, okay? Because it may be the case that if, like, an adversary that is, like, isolated may not be able to provide a proof for a false statement or proof for a statement that it doesn't know a witness for, but with this additional knowledge, seeing additional proofs, it could. So one example could be if proofs are randomizable, right? So for example, the adversary doesn't know the witness for the statement, but sees a proof for that particular statement, randomizes the proof, and sends this as its own proof, right? So in that case, we cannot say that adversary knows the witness. It only was able to randomize the proofs. And this breaks our scheme completely. But fortunately, we have a stronger notion of soundness that takes care of that. And this notion is simulation extractability. So in this notion, we equip our adversary also with an access to a simulator. And this is the simulator I introducing zero knowledge property. So it's a party that is able to provide a proof for a statement even without knowing witness. And in this case, we also require that the simulator is able to provide a simulated proof for incorrect statements. Okay, so let's take a closer look on the simulation extractability. So we have an adversary with access to these two oracles, so random oracle and simulator, and we require it to output statement along with some proof. And as a response with simulated proofs for x, for any x that is picked by the adversary. And we have a game with adversary, and we define the game such that we say that adversary wins if it outputs x and pi such that pi is not a simulated proof for x. So adversary cannot just like say send x to the simulator, get back some pi and output that. Okay, that's not enough for the adversary to win the game. It needs to modify either x or pi. And then like A doesn't know the witness, so we require that our extractor fails here. Okay, so here the extractor is a bit more complicated because it doesn't get only parameters, SRS, randomness, and the queries that A made to the random oracle, but also it needs to know the queries that A made to the simulator. Okay, so let me discuss some issues with simulation extractability. So one is, I mentioned that what if A can output just a simulated proof? What if randomized proofs are acceptable? So here there's first requirement we need from zkSNARK is something called unique response property. Okay, so for adversary it should be infeasible for some parameter k to output two proofs that match on first k inputs, but then are different and both are acceptable. Okay, so basically if two proofs match at first k inputs, then one of them is unacceptable or both are the same. Okay, and the question, another question is how extractor can provide simulated proofs to adversary, and here we require trapdoor-less zero knowledge. So we require that the simulator that there is a simulator able to provide simulated proofs even without knowing a trapdoor. And this may sound strange, but on the other hand, hey, we are in the random oracle model, so we use a property of random oracle programmability to allow simulator, to allow extractor to provide simulated proofs without knowing trapdoor. Yes? Yes, very, very good question, thanks. The question was about proofs of false statement. Yes, so basically simulators we have for zkSNARKs are able to provide valid proofs for false statements as well. So this simulator breaks down? Yes. But like simulator is like a theoretical construct, okay? It's not a real party. We don't have such a real party that is able to program a random oracle, for example, right? And we also assume that we don't have party that knows the trapdoor. Okay? We only need simulator as this construct to be able to show here simulation extractability and also zero knowledge. Okay, so now let's go back to the slide how zkSNARKs are built, and let's take for example a Plonk. So I don't want to get into Plonk details, but let me just state that in Plonk the witness is some 3n elements, okay, which are divided into parts of n, and these elements are encoded into 3 polynomials. Okay. So basically, if we have these polynomials written in clear, then we can also read the witness. Okay. So how do we extract? So let's make an observation that the degree of these polynomials is bounded. Okay. And in case of Plonk, it's like n plus 2. So if we evaluate these polynomials at at least n plus 3 points, different points, then we can reveal their coefficients. So the idea is to let the extractor learn multiple evaluations of these polynomials that have witness at coefficients. Right, so the extractor learns some. So we evaluate polynomials pi at different values of evaluation challenge z, and we gather n plus 3 such evaluations. We do Lagrange interpolation, and we recover the polynomial. Okay, so the technique we are using for extracting the witness is rewinding. So A plays with some random oracle to get challenges, and at some point it gets the evaluation challenge z and sends back evaluation of these polynomials. Okay, so extractor who internally runs the adversary can rewind A. So because A is like a machine, you can like go back in state and pick a new random oracle. And here, by picking a new random oracle means let's pick a random oracle that on the same input as here returns a different challenge, Z2. Okay? So if Z2 is now provided to the adversary, for the proof to be acceptable, A must return a different evaluation of the polynomials pi. Okay? And then the situation continues till extractor learns n plus 3 evaluations. Okay, so how do we know that this procedure actually gives us a witness? So how can we be sure that that if we learn n plus 3 evaluations of these polynomials, then we get the correct witness? And here comes the third requirement, that rewinding-based knowledge soundness. So we say that if it's feasible to extract the witness from the polynomials sent by the prover. Okay. Last but not least, we also require so unique response property. So let me explain why it matters here, and this is because if we allow the adversary to use, say, simulated transcript up to the point after it learns zi, then rewinding may break, because we will need to cheat the adversary on a simulated proof. So on a value of a random oracle, it learned by learning a simulated proof. Yeah. Okay. So and if A keeps asking questions, then here we use the trapdoor-less zero knowledge property. So basically, the extractor can also provide A with simulated proofs, right? Because it may be the situation that as input, the extractor gets all the simulated proofs that adversary learned by querying its simulator, but now we rewind the adversary, we provide it with a different random oracle, so the adversary strategy may change because of the change in the random oracle, right? So adversary may be adaptive to what it sees from as answer as a random oracle. Okay, so to conclude, what makes Fiat-Shamir zkSNARKs simulation extractable? So first we need to answer how extractor can provide simulated proofs. So here we have our trapdoorless zero knowledge property. Then we need to figure out what happens if A can like output randomized simulated proofs, and we have unique response property. And last but not least, how do we rewind? How do we know that rewinding is like a proper technique to learn the witness? And here we have rewinding-based knowledge soundness. And that concludes my talk. I'm happy to take any question.
Any questions?
Yeah.
I think it works.
The definition of simulation-extractability that you use, if I'm not mistaken, in particular, it means that it's non-malleable. Right? The proof system should be non-malleable, otherwise...
So the question was about the definition of simulation extractability. We don't require the proof system to be non-malleable.
Then I can take a proof for like field of 1 and just flip some bits and make it a proof of field of 2. Make the witness.
Oh, okay. So the definition is very similar to, I would say, standard definition for simulation extractability for NISCs, but we also account for Fiat-Shamir transformation, and we explicitly make an assumption about rewinding, and this matters because we may have a situation where the adversary works fine only for a very particular set of random oracle outputs. So if in that case we may not be able to, to make n+3 evaluations. Yeah, I'm not sure that answers your question. I think it doesn't, but so non-malleability, yes, we don't require it, but I think it's like we are close to non-malleability of like interactive proof system. But our definition is like in a non-interactive setting.
Again, what are the examples of the non-simulation extractable systems?
Graph 16, for example.
Yeah.
But Graph 16 is, so we have here like a strong and weak simulation extractability. So in Graph 16, you can re-randomize the proof, but yeah, sorry, you can randomize the proof, but you cannot like get like nothing more than that.
And what's the simplest immunization of Graph 16 that makes it simulation extractable?
Oh, that's a very good question. I'm not sure, to be honest. I think you would need to imply use some framework that would like imply like efficiency loss, but.
Okay. Any more questions? Yes.
Yeah.
It looks that you are using the adversary as a black box, but still giving the random coin to the extractor.
Yes, it's not non-black box extractability, if you're asking.
How that R is useful in the
We let me think. So actually, we don't use R itself, but we use the possibility of rewinding the adversary to a given point in time. But I would say that, okay, so formally, you can think that extractor gets a code, okay? And this code requires some input. And this input to adversary is public parameters, SRS, but also randomness, because randomness tells you what proofs the adversary is going to generate. So you want to recreate inside the extractor exactly the same proofs that were created by the adversary outside the extractor, right? So you need to have like two identical executions, like in like without extractor and within the extractor, right? And since the adversary may use the randomness, like in computing some parts of the proof, that then you need to provide this R.
Okay, we can take further questions after the next talk. So yeah, the next talk has the intriguing title "Counting Vampires," and the rest. This is
Yeah.